Hello, everyone. Welcome back. So we are going to be finding a new way to multiply two vectors. This is now called the cross product, which is different than the dot product, which was the previous section. Before we do the cross product, I need to teach you some math that maybe you haven't seen before. And we're going to find something called the determinant of a matrix. And the determinant of a matrix is, we're going to start in two dimensions. So the notation, it looks like absolute value. And we're assuming A, B, C, and D are all real numbers. I'm missing an R. Determinant there we go, of a matrix. And when it's a 2 by 2 matrix, meaning I have 4 elements, the determinant is going to be also the notation det of the matrix. I'll say capital A. And this becomes A times D minus B times C. So for example, let's say I have a matrix A, 1, -2, 3, -4, and I want to find the determinant of matrix A. That's going to be 1, -2, 3, -4. And so that's going to be 1 times -4 minus -2 times 3. Now be careful of the double negatives here. Obviously, that's going to become an issue. So that's -4 plus 6. So in this case, the determinant is 2. This is for a 2-dimensional one. A 3-dimensional one, it becomes much more complicated. In 4 dimensions, even more so, and so on. But we're just going to go up to a 3-dimensional one. So I'm going to do this. So we'll say matrix A is A, B, C, D, E, F, H, I, F, G, pardon me. F, G, H, and I. So to define the determinant, we're here. And what I'm going to do is I'm going to use the ABC to do this. There's so many different ways that we can do this, but I'm going to really stick to this. And I'm going to start with A, and I'm going to take this row and this column, and this is going to be A times the determinant of what's left, E, F, H, I. Minus, and there's a reason there's a minus that I'm not going to get into. Next up, I'm going to use the B now. So this is going to be B, and it's going to be the determinant of what's left over. D, F, G, I. Back to plus C times. And then now I'm going to use C. And I'm going to write down what's left over there. D, E, G, and H. All right. So overall, my determinant is going to be A times E times I minus F times H minus B, be careful the minus, of D times I minus F times G plus C times DH minus EG. And you can see, and we're going to do this process over and over and over again. Oops. And now we are going to do the cross product. So let's walk through this. Given two non-zero vectors A and B, it is very useful to be able to find a non-zero vector C that is perpendicular to both A and B. So this cross product, and you can see how incredibly messy this is. But you can just imagine that that's kind of what I just did just a few minutes ago. But I did it using a determinant. And one of the interesting properties is that both vector A and B, doesn't matter the angle between them. However, the angle between each A to A cross B and the angle between B and A cross B are always going to be 90 degrees. It's always going to be a right angle, which is super cool because there are going to be times when we need, we're going to need an orthogonal vector to to vectors that we have. All right, and so the big one is here. A cross B is going to be all of this here. And this is how I'm going to focus for the rest of the lesson today. All right, so A cross B, now the very top row are our unit basis vectors, the I, the j, and the k. Each of those are in the direction of, I is in the direction of the x coordinate, j is in the direction of the y coordinate, and k is in the direction of the z coordinate. And then it's the first variable, or first vector, A, its components, 1, 2, and 3. And then the second one, and what we're going to do is we're going to do the determinant based on I, then j, then k, and we're going to end up with a new vector as we do this. So let's set this up. So A cross B is going to be I, vector j, vector k, and then 1, 3, and 4, and then 2, 7, -5. And this becomes vector I. So now I'm doing, if you remember just a minute ago, I'm now doing here and here. And what's left is 3, 4, 7, -5. Remember, it's minus j. And now I'm going to plot out the row and column of vector j. And that leaves me with 1, 4, 2, -5, plus vector k, times, and now I'm going to plot out here and here. And what's left is 1, 3, 2, and 7. And that's going to get us to vector I times 3 times -5 is -15, minus 28, minus vector j. That's going to be 1 times -5 is -5, minus 2 times 4, which is 8, plus vector k. 1 times 7 is 7, minus 2 times 3, which is 6. So that's going to give us -43. And you can write it with the i's, the j's, and the k's in there still. And that's going to be minus -13, so that's just going to be a positive 13. And then 7 minus 6 is 1. And here is our new vector, A cross B. And once again, notice we now have a new vector. All right, I'm going to do the example 2 underneath this. So A cross B is vector I, vector j, vector k, and 0, 3, -4, 2, -1, and 5. So once again, I'm going to blot out here and here to get vector I. And what's left? 3, -4, -1, and 5. Minus j, remember the minus. That brings us to here and here. And what's left is 0, -4, 2, and 5, plus vector k. I am left with 0, 3, 2, -1. And so let's keep going. Vector I. 3 times 5 is 15. Now be careful, minus -1 times -4 is +4, so there's still minus in there. That's 3 minuses. Minus vector j. 0 times 5 is 0, minus -8, so that's going to be 0 plus 8 plus vector k times 0 times -1 is 0, 0 minus 6. 15 minus 4 is 11. Actually, I'll do it like I did the other one. I'll do it here. 11, comma, -8, -6. And there you have the cross product. All right, let's keep going. So find two unit vectors that are orthogonal to this vector. All right, so let's do this. We know that the cross product of the two will be orthogonal. I, j, k. And we already learned how to find a unit vector. We have to find the magnitude and divide through by it to make it a unit vector. 3, 2, 1, -1, 1, 1, 0. So this is going to be vector I. Once again, or here. 2, 1, 1, 0, minus vector j. And we're left with 3, 1, -1, 0, plus vector k. We are left with here 3, 2, -1, 1. And I'll continue down over here. So this is going to give me 2 times 0, which is 0. So this is I. 0 minus 1 times 1 is 1. Minus j. I'm going to say it every time. Don't forget it's minus. Oops. And that's going to give us 3 times 0, which is 0, minus -1. So that's 0 plus 1 plus vector k. That's going to give us 3 times 1 is 3, minus -2 is +2. So that gives us -1, comma, -1, comma, and 5. And we're not done. I have to find its magnitude. So that's going to be the square root So that's going to be 1 plus 1, that's 2, plus 25 is root 27. So a unit vector that's orthogonal to both the vector 3, 2, 1 and the vector -1, 1, 0 is going to be 1 over root 27, -1, -1, and 5. And they want 2 unit vectors. So here's one of them. And a vector in the opposite direction is also going to be orthogonal to both of them and a unit vector. So 1 over root 27. And I'm just going to change all the signs. 1, 1, -5. Both of these are going to be orthogonal to both of the initial vectors that were given. All right, so we want to show that vector A cross vector A gives us our 0 vector, or any vector in 3 space. So let's set this up. So we can squeeze this in here. Vector I is going to be, and once again, here. So this is going to be A sub 2, A sub 3, A sub 2, A sub 3, minus vector J, A sub 1, A sub 3, A sub 1, A sub 3, plus vector K, and for vector K, I'm left here and here. So A sub 1, A sub 2, A sub 1, A sub 2. This is going to give us vector I times A sub 2, A sub 3, minus A sub 2, A sub 3, minus vector J, A sub 1, A sub 3, minus A sub 1, A sub 3, minus vector K, A sub 1, A sub 2, minus A sub 1, A sub 2. And we can clearly see that that is going to be 0, 0, 0, which is the 0 vector. Kind of cool. All right. So the vector, so we have a new theorem. The vector A cross B is orthogonal to both A and B. I've already mentioned this theorem. In fact, we've already used this theorem. I think these notes need to be, this theorem needs to be moved up a little bit. All right. So first off, I need to find, example 5, find a vector perpendicular to the plane that passes through the points P, Q, and R. And first what I need to do is I need to build my vector. So I'm going to build a vector PQ. And if you remember from the previous video, that's going to be -2 minus 1, 5 minus 4, and -1. -1 minus 6. Yeah. All right, so this is going to give us the vector -3, 1, -7, and then PR is going to give us 1 minus 1, and -1 minus 4, and 1 minus 6, which is 0, -5, -5. And I'm going to now do the cross product. So let's see, PQ cross PR is going to be I, J, K, -3, 1, -7, 0, -5, -5. All right, let's see what we can come up with. I is going to be 1, -7, -5, -5. Minus, again, it's minus, don't forget. J, which is here and here. So I am left with -3, -7, 0, -5, vector K. And I am left with -3, 1, 0, -5. So that gives me vector I. And 1 times -5 is -5. Now notice it's -5 times -7 is -35, or +35, but it's going to be -35, comma. And now we're going to have, not comma, close parenthesis, minus J. -3 times -5 is 15, minus 0, plus vector K. -3 times -5 is +15, minus 0. So we end up with the vector -40, -15, 15. So this is an orthogonal vector to both of these vectors that are in the plane that contain the points P, Q, and R. Now, very nicely in these notes, we have a new theorem. So let's talk about our theorem. And I'm going to keep, no, I'll show it in just a minute. So our theorem here says if the angle theta is the angle between vector A and vector B, then the magnitude of the cross product of A and B is actually the area of the parallelogram that you see to the right here, which is super cool. Now, I do want to point out, we don't need to know the angle and the magnitude of A and B and all that. We just need to find the cross product and find its magnitude, and that will give us the magnitude of the entire parallelogram. Now, very nicely, you'll notice that these 3 points here are the same 3 points up here. Let me show you what I mean. Points P, Q, and R are the same P, Q, and R, which is awesome, and it's going to save us quite a bit of work because we don't have to actually do the cross product. We already have the cross product. So the vector -40, -15, 15 is the cross product. So really all I need is the magnitude. So let's find the magnitude. So 40 squared plus 15 squared plus 15 squared is here, square root of 2050. All right, now that is the area And I'm going to draw my own parallelogram here. Let's use another color. So I'm going to call this P, this will be Q, this will be R. And what we just found is the area of the entire thing. Now they want us to find the area only of the triangle that makes up PQR. That is this area here. And I want to point out that that area is exactly half of the area of the parallelogram. So the area of the triangle is going to be root 2050 divided by 2. So let's see what approximation we get with that. Square root 2050 equals divided by 2. And that gives us about 22.64 square whatever the unit is. And so we don't know what the unit is. That is our answer. I hope that was helpful.